second-year PhD student at Warwick, and I will try not to keep you from coffee for too long. I know I need some more, so. Okay, so a bit of a change of topic from kind of the other bits that we've been seeing in these sessions. I'm going to talk about white dwarf ages in particular, and kind of how we can use them as age determiners and also for star formation rates and histories. So obviously the fundamental thing about white dwarfs is that they cool very predictably with time, with a few small caveats we'll get into. And therefore their temperature is fundamentally linked with their age, which makes them quite good. We don't need that much observational information to actually kind of get their ages in that sense. So we've got a little layout here of kind of how we can calculate it. If we observe a white dwarf at a particular mass and we know its temperature, we can calculate very easily its main sequence mass and therefore its main sequence lifetime. We can get its whole pre-white dwarf age and its white dwarf cooling time. All of these are pretty well established and we have lots of good models for those. The problem is, even if you can calculate all of those, ignoring any systematics, we get to the point where we don't know things like whether it merged and whether that affected its lifetime. We don't know whether it's got any core crystallization, whether that's delayed its cooling, which would delay how we're viewing it and therefore what age we view it as. So we think we can do all of these things, but we were kind of exploring actually how well we can do them at the minute. So one of the first things that we need to determine in order to get good white dwarf age determinations is the effects due to crystallization. So as a white dwarf core cools, it will start to crystallize over time. And in ordinary crystallization, this goes from the core all the way outwards and halts cooling because basically the crystallized material sinks, it releases gravitational potential energy, and although white dwarfs have no nuclear energy, this energy release will slow down or even halt their cooling. We've also now discovered more recently, in a paper from last year, that you can effectively get distillation as well. So you can have small crystals that will start to rise and melt and sink and freeze in this kind of constant cycle, which can produce even more gravitational potential energy than we previously thought. And this can actually halt white dwarf cooling for up to 9 gigayears in some cases, which throws off basically any age determinations you might think you have, because you've got to factor in for what's going on beneath the surface. The other issue that we're currently grappling with is the spectral evolution of white dwarfs. So all of our white dwarf cooling models basically depend on the atmospheric composition that we observe of the white dwarf, whether it's hydrogen or helium. And the issue is that as white dwarfs start to cool, any changes in convection, diffusion, accretion of other material, it can start to stir up the layers, the uppermost layers of the white dwarf's atmosphere, and effectively change its atmospheric composition, which means that we would have to recalculate all the models. The effect of this on ages of white dwarfs is very non-linear. It's not just a case of, oh, if it becomes helium, it's older. That would be too easy. So we need to know how likely white dwarfs are to either evolve their spectral type in the future or whether they have in the past. And we know about 22% of white dwarfs in this temperature range do that, but it's very hard to tell for any individual white dwarfs. So we can do it on a population. Individual objects, much trickier. So what I've been doing is trying to create a simulation of the local white dwarf population. We wanted to look at the ages, whether we could do age determinations, and whether we could recover the star formation rate of the local Milky Way. And I've been using a Gaia DR3 sample, which has about 1,000 white dwarfs in it. We give my simulation a assumed star formation rate, then we evolve all the stars through time, and we compare those to the Gaia observational parameters to see how well they fit. So we have quite a few different star formation histories. We've got a constant one, we've got one with an early peak, a late peak, and then the one that says this work is basically we calculated the ages of all the stars and used that to see whether it was self-consistent. So a lot of people have been talking about the uncertainties on this kind of age determination, and we have a lot. Basically, every step in my simulation here has a systematic. So we were also trying to work out how much they're affecting age determinations too. And yeah, a lot of models, a lot of different systematics. That was really fun to deal with. So we looked at 3 different methods of doing this, whether there was any difference in the underlying assumptions, any differences in the results that we got. So we looked at the white dwarf luminosity function. We looked at the absolute Gaia G magnitude distribution. And then, as I mentioned, we also calculated the direct ages of all the white dwarfs in the sample. And the result that we get for this, which we fed back through our simulation, is that we see this much higher star formation rate in the more recent Milky Way history, with about half as much star formation in the past, in the early Milky Way. So if we are looking at the kind of star formation histories that we found and the ages, we basically found that if you look at the direct age calculations, I think as a couple of the previous talks mentioned, the oldest object kind of sets the limit here. But the oldest object that we found was about 12 gigayears or even older, with, as you can see here, very large uncertainties due to every single step in that simulation that I showed you. So the actual precise population age can't really be constrained with the direct age method, even if you can technically get individual ages. But the other 2 methods, which are kind of more defined by where the drop-offs are in these distributions to get the population age, these were much more well-defined. So if you start using populations rather than individual white dwarfs, you can get quite good constraints. So we found, in line with previous white dwarf studies, 10.6 gigayears plus or minus 1, which we were quite happy with, especially compared to plus or minus 4. So direct age might seem like the more obvious choice because you are directly aging the stars, you're not making any assumptions. But yeah, for individual stars, it gets kind of murky. We do need to do these population studies. And if we're looking at the star formation histories that we found, which was kind of the primary work that we were looking at, I've got here a plot of the different star formation histories and the reduced chi-squareds that we calculated against the observational fits. And the first thing that you might notice is that the error bars on these are massive, which basically means we actually can't tell the difference between any of those 4 star formation histories using these methods. We can start to say which ones we think might be worse. For example, ones with really early peaks don't seem to fit the local Milky Way at all. It definitely favors those with later peaks or constant star formation, but statistically we can't disprove any of these star formation forms, which is a bit annoying. The other thing, as I mentioned, the issues with direct age calculations are, again, the really large uncertainties from all the models. This is basically within 2 sigma of constant because of the large uncertainties, especially from small number statistics with this sample. The highest bins only have about 120 stars in them. So again, you can sort of use whatever star formation history you would like with the 40 parsec sample, and you'll get a pretty decent fit. We looked at what the modeling assumptions were and kind of which of the systematics were having the largest effect on our results. And we found that the cooling age uncertainty, so the white dwarf cooling time, is the largest uncertainty aside from Gaia observational errors, that is. The metallicity, which you have to assume because we don't have that information from white dwarfs very easily, is the next highest one. So we had to assume a solar-like metallicity with some Gaussian spread on it for all of our objects. And then determining whether white dwarfs underwent any binary evolution or experienced a merger in their past. Again, it's quite difficult to tell that from the white dwarf remnant, whether they had that in their past, but that can also have quite a big impact on how long they've been cooling for and their observed age. So what we're actually looking to do next is, fundamentally, this just needs more stars. We have 1,000 in the 40 parsec sample, and my work at the minute is going up to 100 parsec, which has about 10 times that, and then obviously next year with DR4, hopefully we'll have even more. That will introduce some other problems. We'll have to start de-reddening everything. We'll have to start looking at other extinction effects and things like that. But we're hoping that the increase in the sample size will overcome any of these extra assumptions that we have to make. And we're also going to be working on just how we reduce these large uncertainties. Can we get some better white dwarf cooling grids? Can we start to identify which stars have undergone binary mergers, things like that, that would help reduce the systematics on the problem, which is fundamentally the biggest limiting factor at the minute. So I think white dwarf cosmochronology is possible, very much so. And at the minute, it's kind of more the models and the systematics that are the issue, less than the observations. We have plenty of white dwarfs, we have plenty of well-defined and spectroscopically followed up white dwarfs. We just need to put some groundwork into refining the errors and particularly working out ways to determine specifically which individual stars have experienced which processes, rather than having to make percentage assumptions for the whole population. So yeah, that's everything then. If you've got any questions, I'm happy to take them. Thanks for listening.